Right now, at the center of the Milky Way, something is eating. Not metaphorically, not slowly. There is an object 4 million times more massive than our entire Sun, compressed into a region smaller than the distance between Earth and the orbit of Mercury. And it is consuming gas, dust, entire star systems, pulling them across a boundary from which nothing, not light, not information, not any signal of any kind, ever returns. We have known it was there for decades. We have named it. We have mapped the stars orbiting around it. We have even taken its photograph. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, the supermassive black hole at the heart of our own galaxy, and the world looked at it for a day and moved on. What the world did not pay attention to was what astronomers were quietly saying to each other in the weeks and months that followed. But the more they studied it, the less it behaved the way it was supposed to. That some of the measurements coming back from the galactic center were not just surprising. They were, in the careful, restrained language of scientists who do not like to overstate things, deeply inconsistent with current theoretical models. And that something, somewhere in our understanding of black holes, may be fundamentally broken. Let's establish what we thought we knew, because the foundation matters before you can appreciate how badly it has cracked. Black holes come in different sizes. Stellar mass black holes form from collapsing stars and weigh anywhere from a few to a few dozen times the mass of our Sun. Then there are supermassive black holes, the monsters anchoring the centers of most large galaxies, ranging from millions to billions of solar masses. Sagittarius A sits at 4 million solar masses, which makes it mid-sized as supermassive black holes go. The one at the center of the galaxy M87, famously imaged before Sagittarius A in 2019, is 6.5 billion solar masses. Sagittarius A is comparatively modest. What it is not, however, is quiet. For most of its modern history, Sagittarius A has been classified as a low-luminosity active galactic nucleus, a sleeping giant. It accretes matter at a rate far below what you'd expect from a black hole of its mass, meaning it eats slowly relative to its size, and it doesn't produce the ferocious jets of energy that more active galactic nuclei do. Astronomers described it as surprisingly calm for something so massive, an underachiever. That description started falling apart in 2019, and it has been falling apart faster ever since. In mid-2019, astronomers monitoring Sagittarius A in near-infrared light, using the Keck Observatory in Hawaii, recorded something unprecedented. The black hole abruptly brightened to twice the highest flux ever previously recorded. In a single night, it became roughly 75 times brighter than its typical state. This was not a small fluctuation. Sagittarius A is known to be variable, flickering in brightness as clumps of material spiral inward and heat up near the event horizon. But this event was categorically different in scale. It was, in the words of the lead researcher Andrea Ghez, the biggest brightening event ever recorded from Sagittarius A, and nobody had a clean explanation for it. Several possibilities were proposed. One involved a gas cloud called G2 that had been tracked on a close approach to Sagittarius A back in 2014. When G2 was first discovered, some astronomers predicted that its passage near the black hole would trigger a dramatic feeding event as material was stripped from the cloud and consumed. That didn't happen in 2014. Sagittarius A barely reacted. But the 2019 flare reignited the question of whether the black hole was finally digesting material from that encounter years after the fact, with the delay caused by the complex dynamics of how gas circulates in the chaotic environment of the galactic center. Others proposed that a star called S022, which completed its closest approach to Sagittarius A in 2018, may have donated material during its perihelion passage that triggered the brightening months later. Neither explanation is fully satisfying. Neither fully accounts for the magnitude of what was observed. And crucially, it was not the last time it happened. Follow-up monitoring in subsequent years has revealed that Sagittarius A is flaring with a frequency and intensity that challenges its prior reputation as a dormant, well-behaved black hole. It is becoming increasingly clear that what we thought was a sleeping giant was simply a sleeping giant between meals, and it is waking up. But the flaring is only one piece of what is unraveling. Because the Event Horizon Telescope image, for all the celebration surrounding its release, contained something quietly alarming embedded in the data. Sagittarius A was extraordinarily difficult to image compared to M87, not because it is farther away. It is actually much closer, sitting only around 27,000 light-years from Earth compared to M87's 53 million light-years. It was difficult because it was moving, changing, flickering so rapidly that the image had to be constructed from thousands of individual observations stitched together using algorithms that accounted for the constant variability. The gas and plasma swirling around Sagittarius A orbits the black hole in a matter of minutes. Not years, not days, minutes. The material nearest the event horizon is moving at a significant fraction of the speed of light, completing a full orbit in roughly 20 to 30 minutes. For M87, that same orbit takes days. This difference in dynamical timescales is not just a technical imaging challenge. It tells us something profound about the physical environment around Sagittarius A and the forces operating there. And what it tells us connects directly to one of the deepest unresolved tensions in theoretical physics. General relativity, Einstein's theory of gravity and the foundation of our understanding of black holes, makes very specific predictions about the geometry of space-time near a black hole event horizon. Those predictions have been tested in many contexts, and they hold up remarkably well. But they break down at the singularity, the point of infinite density at the center of the black hole, where the equations produce results that are mathematically meaningless. Physicists have known this for decades. The singularity is widely understood to be a sign that general relativity is incomplete, that at extreme enough densities and curvatures, a deeper theory, one that reconciles general relativity with quantum mechanics, must take over. We do not have that theory. We have candidates: string theory, loop quantum gravity, various other frameworks that attempt to merge the two great pillars of modern physics that have stubbornly refused to be unified for nearly 100 years. But we have no confirmed theory of quantum gravity. And without it, the center of every black hole in the universe, including the one 27,000 light-years away from you right now, remains a place where our understanding of reality simply stops. What makes Sagittarius A uniquely valuable is that it is the closest supermassive black hole we will ever have access to. Every improvement in our observational technology, every new generation of telescope, every upgraded detector, brings us closer to probing the environment near its event horizon at resolutions that begin to test not just general relativity in the abstract, but specific quantum gravitational effects that different competing theories predict differently. The next generation Event Horizon Telescope, currently being planned with additional stations across the globe and in space, will achieve resolutions that could detect deviations from pure general relativity at the level of a few percent. If those deviations are found, if the shadow of Sagittarius A differs even slightly from the shape that Einstein's equations demand, it will be the first observational crack in a theory that has held for over a century. The first direct evidence pointing toward whatever comes next. There are researchers who believe that crack is already visible in the existing data, that the rapid variability, the unexplained flares, the magnetic field structure near the event horizon captured in polarized light observations in 2024 are collectively pointing toward physics that standard models of black hole accretion cannot fully explain. That something in the environment closest to the event horizon is behaving in ways that hint at new physics. That hint is not a confirmation. It is not a discovery. But in the history of science, hints have a tendency to become hard evidence slowly, then all at once. At the center of our galaxy, 4 million solar masses of compressed space-time is flickering, flaring, consuming, and bending the fabric of reality into shapes our mathematics struggles to describe. It has been there for billions of years. It will be there for billions more. For the first time in history, we have instruments sensitive enough to ask it questions that matter. The answers, when they come, may not just tell us what lies at the heart of our galaxy. They may tell us what lies at the heart of reality itself. We thought we understood black holes. Sagittarius A is making sure we know that we don't. And that's it from this video. See you in the next one.